Enjoy. Eric,
Okay.
enjoy it too.
Thank you.
See you later.
See you later. Well, Lena was right about one thing, that we are friends. But for the rest, she was overestimating me. I think it's very nice to be here again. I work as a curator in a small museum in the Netherlands, in the eastern part of the Netherlands. Perhaps you have heard of the city of Enschede, near the German border. And there's a small village, that's where I work. And it is the fourth time now that I am in the city of Opole. And I think it's very nice, you could say that I more or less has fallen in love with the city of Opole. So it's always very nice to be here. And to meet you, of course. Well, these series of talkings with each other is about paleoecology. And, well, ecology is a common term. Perhaps somebody could tell us what ecology is. How would you define that? Can somebody define the term ecology?
Ecology is a science about relationships between organisms or species, for functional relationships, not feeling.
Yeah, you're right.
And their environment.
And their environment, the interactions with their environment. And perhaps I think it's interesting because the person who invented the term ecology was Ernst Haeckel. You have heard of Ernst Haeckel, I think. He was you could say he was a German medical doctor and a zoologist, and he was Darwin's advocate on the European continent. So he's a zoologist dealing with evolution, but he invented the term ecology, Ernst Haeckel. And ecology is, of course, very important because living organisms, life, right from the start, they have an interaction with their environment. And that's why I want to look in this first talking about the origin of the first ecosystems. How did it start? And you are, of course, familiar with these kinds of things. Hello, come in. When you talk about ecology, it always starts with something like this. You are familiar with a picture like this, I think, the so-called food chain, but it's not quite the reality, I think. What, in other words, what's wrong about this picture? It's too simple, it's far too simple. There are much more interactions between organisms and so on and their environment, and it's more like this. It's more closer to reality. We can call that a food web, the interactions between several organisms and their environment. And so that's where it is about. You cannot think about life without food webs, without ecology, and this has been in the history of the Earth for all times. But let's have a brief look at the time schedule. This is a time schedule, the history of the Earth and life. The Earth is about more than 5.5 billion years old. And a few important things are here. The cooling of the Earth's surface, of course. The origin of the oceans and the atmosphere. The origin of the moon is interesting. It's a piece of the Earth, which because of an asteroid impact got loose of the Earth. The earliest life forms are, of course, important. We will talk about them, because with the earliest life forms, of course, ecology started already. The origin of an oxygenated atmosphere is very important, so that the oxygen played an important role in the life. And then there are some other things. Perhaps you have heard about the Cambrian explosion. I mean, there was a time then suddenly people starting finding fossils about 550 million years old and younger. So suddenly they were there, it seems, so that's why they call that Cambrian explosion. But if you look at the history of the Earth itself and the origin of life, then you see that relatively the Cambrian explosion started much later. So it's to say that most of the history of life, it were only simple life forms. So the real evolution, the explosion of evolution started much later. So let's look at how it is now in the atmosphere of the Earth. And the present day atmosphere is about 75% nitrogen and 21% oxygen. But that is a result of the interaction of life forms with the Earth. So we have to go back in order to understand something about the origin of life. We have to go back around the time that the Earth started to evolve. And when the solar system started to evolve, so when the planets evolved, in the planets themselves, there was a selection of the chemical elements and the chemicals and the minerals according to their specific weight. Perhaps it's logic, but it has to do with gravity, of course. So in the protoplanet of the Earth, there was a selection of minerals, chemicals and chemical elements according to their specific weight. And that's, in a way, the reason why the Earth looks like this. We can speak of an anatomy of the Earth. I think it's more or less familiar to you, or completely familiar to you, but it's very important because the Earth in itself, you could consider that as a nuclear reactor. So there are nuclear reactions. In the inner core of the Earth, there is a decay of radioactive uranium, and that's very important. If that would not take place, there would not be life, because the energy which is coming free from the decay of radioactive uranium, it's that heat that is coming from it is the cause of the convection streams of the liquid material in the Earth mantle. And that's very important, because if that would not take place, that uranium decay in the inner Earth, you would not have continental drift, for instance. Because thanks to this phenomenon, thanks to this uranium decay and the energy, there is material from the inner Earth coming through the ocean floor. And that's very important. Without that phenomenon, there would not be life. Because it's in this scheme what you see, how material from the inner Earth is coming into contact with the seawater at the bottom of the ocean, what you see by number 1. And that chemical reaction from the new minerals coming to the surface with the seawater is very important. And that change of minerals is called serpentinization. And this is what is happening from a chemical point of view. By the way, these slides will be available later. So of course you can write those formulas down, but I don't know if it is necessary, but it's of course up to you. But this was new for me also. That mineral, it's called olivine, reacts with the water from the ocean and changes into serpentine. And what is not in this formula is that there is not only serpentine, but hydrogen gas is also coming. So there is free hydrogen available, H2. So it's serpentine plus H2. And so there is H2, hydrogen, available at the bottom of the sea. And that is very important. Without this reaction, there would be no life on Earth. There would not be ecosystems also. So there would be no paleoecology also. Because that free hydrogen, that free H2 makes this possible. You could call that free energy. Eh? Life is about energy. We stay alive because we can use energy. It's necessary to stay alive. So the first life form, the first proto-life, should have energy available to evolve. And thanks to this chemical reaction, that is possible. And there are still methane bacteria, perhaps you are familiar with them, methane bacteria who are getting energy because they do this. They change hydrogen and carbon dioxide, which is also available in the ocean waters. They change it into methane and water. And this is delivering energy. So this is, so to say, the oldest metabolism of living forms. This chemical reaction can also take place outside living forms. That's why it's called non-chemolithotrophic also. That is to say, this reaction can evolve also without bacteria. And this system is still practiced by bacteria who are living in strange places, because this reaction is done by bacteria who don't like oxygen. So the bacteria who do this still today are living in extreme conditions, like in the deep ocean or in the stomach of a cow. Without these bacteria in the stomach, cows could not eat grass. The bacteria do the work for them. So in extreme environments, these bacteria are still alive. So that is one of the key conditions that you will need on Earth to be able to get life, to make life possible. So the earliest atmosphere looked very strange. We would look very strange at it. Here are the gases which were there. And there was no oxygen. That's very important. We are adapted to use oxygen, but there was no oxygen. So the first life forms, the bacteria, were without oxygen. And like I said, there are still places on Earth where you have these extreme conditions. For instance, in the Yellowstone Park, there's a water temperature about 85 degrees Celsius. In this water there is no oxygen, so these strange bacteria, thermophile bacteria, they can stand the heat, are living in these conditions. So